In this lecture, let's briefly review the I2C serial interface and then go on to implement code to communicate with a digital thermometer. So first, let's start with a quick review. The I2C interface needs only 2 wires. Now the top speed is rather low, but it's great for reducing external pin usage. In addition, it's truly a bus. Each device on the bus has a unique address. Specifically, each address consists of 4 bits determined by the type of device, then 3 bits determined by the actual electrical wiring. Typically, each device will have 3 pins on it that you can configure, and this is in fact the case for the digital thermometer we'll communicate with. Recall also that this is an open collector interface. We need 2 pull-ups on the SCL and SDA line. The protocol always begins with a start bit. It consists of 8 data bits followed by an acknowledge, and a transmission is ended by a stop bit. There are 2 types of transactions: a write transaction, a start, the address with the write bit cleared to a 0, data to be written, then a stop. A read transaction, beginning with a start bit, the read address with 1 for the read-write bit, data read and an acknowledge to request more data by the master, data from the slave, and no acknowledge to conclude the transaction, a stop from the master. We can use a series of primitive interface functions: start, stop, put, and get to communicate with a given device. Higher level functions, writing 1 or 2 bytes, reading 1 or 2 bytes, are implemented simply by beginning with a start, sending the address here with the write bit set, data to be written, and a stop for a 1 byte write. In the case of a read, a start, putting out the address with the read bit set to a 1, getting data to be read with a no acknowledge, signaling the end of the read, and a stop. Armed with this knowledge, we're now ready to begin looking at a specific digital thermometer and interfacing to that. Having briefly reviewed the I2C protocol, now let's take a look at a specific implementation using the DS1631 digital thermometer. As you recall, the I2C bus is open collector, so we need 2 pull-up resistors on the SCA and SCL pins, and we need to configure an address. The chip has 3 address pins, and we need to tie those address pins somewhere. In this case, we've picked ground in order to pick a specific address. We'll look at some selected aspects of the thermometer's behavior rather than exercise all the available functionality. In particular, let's take a look at these specific pieces. We would like to be able to do 2 simple things. First of all, we would like to make use of an 8-bit write. Doing that, we can access the configuration register and configure the thermometer to our desired commands. Second, we'd like to do a 16-bit read, where we read back a 16-bit or 9-bit temperature value embedded in a 16-bit string. So in order to do those 2 things, let's look first at the address byte that both read and write transactions are required to send. For the DS1631, the top 4 bits of the address are 1001 for this class of device. The next 3 bits are those 3 address bits. Since we've wired all 3 pins to ground in this example, those 3 bits will be ground. And then last but certainly not least, the read-write bit will specify whether we're doing a read or a write. In the most straightforward case of doing a write, here's what a transaction will look like. As always, we begin with a start. We move immediately to sending that address with the write bit set to a 0 and receive an acknowledgement from the thermometer. Next, we're going to send the command byte, an 8-bit value. In this case, that value is hex AC to say we'd like to access the configuration register followed by an acknowledgement from the thermometer. Finally, we send 8 bits of data to actually configure the thermometer, get an acknowledgement, and then conclude the transaction by sending a stop. The final transaction that we'd like to make use of is a 16-bit read where we can read back the actual temperature data. As always, the transaction will begin with a start, follow with the I2C address. The 0 is set to indicate this is a write, and then we'll see the acknowledge come back from the thermometer. We'll send it a command byte. Now this is a write, not a read. Therefore, when we send it a command byte, we're not allowed to read anything in return apart from an acknowledgement saying that the thermometer received that command. The command in this case is AA, saying we would like to read the temperature register. Next, instead of sending a stop, we can send them something called a restart, the equivalent of a stop followed immediately by a start. By starting a new transaction but maintaining control of the bus, we can then address the thermometer again, but this time come back with a read transaction, and the thermometer understands that following that write will be the read that's enabling us to gather the temperature information, and that responds with an acknowledge. We then read the most significant, followed by an acknowledge, the least significant, and don't acknowledge that last byte saying we read enough data, at which point we issue a stop and finish the transaction. So notice that pattern, which is something a bit new. We start with a write transaction and tell it what we'd like to read, and then we follow immediately after a restart with the read in which we read the requested data. That's a very common I2C pattern. However, before we're allowed to read that temperature, we do need to send one last type of command, a standalone command, which simply tells the device to begin converting the temperature. We can send it a start or stop continuous conversion command, after which we're free to read that temperature. Let's look at writing code to implement those 3 classes of transfers using the functions we've discussed thus far. First, we'll do the standalone command to start continuous operation. This is just a 1-byte write. We send the address, 1 byte indicating a hex 51 start continuous, and a stop. To do that, of course, we need to know what the address of the DS1631 is. We'll define it as hex 90, the device type 1001, 3 zeros based on pulling the 3 address pins to ground per our schematic right here. We'll want a handy definition, hex 51, for the command we're going to send, and then it's simply time to go and send that command. Write 1 byte to the I2C bus to a specific address with the data start convert hex 51. That completes the write command. Next, let's look at writing some configuration data using a command of ECE to access the configuration register using a 8-bit write. Again, the address and 2 bytes, the command and then the data. Therefore, our code is, of course, write 2 bytes to the address we've determined earlier, send it that command of ECE accessing the configuration register, and then send 8 bits based on the command we want to implement. Finally, recall that 16-bit read starts with sending the address and a command byte, and then immediately following that, the address with the read mode this time, and reading back the most significant, then the least significant byte. That is, we're doing a 1-byte write followed by a 2-byte read in order to read the current temperature. So of course the code involves a 1-byte write where we send it that read temperature command, an AA. Then we're going to read 2 bytes, the high byte and low byte of the temperature, and then simply combine those bytes together and return it.